Thank you so much, Loretta. Thank you to the organizer for having me the opportunity of presenting my work, well, my PhD thesis in this case, because now I'm a postdoc at the one group at the UNC in Chapel Hill. But this work was developed in the framework of the Perovskites project, which is an European project basically focused on perovskite material for X-ray detection. And actually, my task in the project was to study the effect of the mobile ions and how on how these species may influence the dark current stability. This work was developed at the Institute of Advanced Materials in Spain, at the Universidad Jaume I. And I would like to start with this brief introduction about how we are surrounded by radiation source. We are exposed to it constantly. And of course, we can see that there is ionizing radiation, non-ionizing radiation. But today, I will focus my attention only on ionizing radiation because X-ray and gamma ray has many applications in medical diagnosis, medical treatment, as security control at the airport, and so many other. It's quite extensive, the application of these X-ray, gamma rays, ionizing radiation. And in order to use and to apply this source, we need to, of course, measure them. And for that, we need radiation detectors. And in the field of X-ray detection and radiation dosimetry, which is the science dealing with the design of these kind of devices, is quite extensive as well. It's a complex interdisciplinary field. And for that reason, today I only focus my attention in the solid state detectors, because solid state detectors can be classified depending on how the interaction of how the conversion of X-ray into an electrical signal is made. And basically, the standard one are the inorganic scintillator, which use the indirect conversion process. In this process, we can basically have the X-ray coming to the material, and the X-ray is first converted to visible light, and then the visible light is converted into an electrical signal. And the second case, the p-n junction, which is based in semiconductor material, germanium-based, silicon-based, we can observe this direct conversion, which is for saying more reliable, because you have like apply a reverse bias, and you can convert the X-ray directly into an electrical signal by collecting charge. So basically, of course, most of them and both technologies are used nowadays, but we found some disadvantage or drawbacks in the use of scintillators, because in order to absorb X-ray, we need to use thick layers, but in order to avoid optical crosstalk, we need to use thin layers. So this kind of non-proportionality, or this kind of trade-off between the sensitivity and the resolution of the device, is one of the disadvantages of indirect conversion or scintillator materials. And on the other hand, we have the use of the direct conversion of the semiconductor materials, which present excellent photoabsorption efficiency, good energy resolution, and is one of the fastest responding detector in the market. Of course, in order to use those devices, they need to fulfill certain properties. Some of the properties I have added here in this slide. You can observe that these devices works under higher electric fields, so we need to use material with high atomic numbers. Then we need a good, of course, any device for this purpose need to have a high efficiency of conversion, spatial resolution, which is connected to the quality of the X-ray image. And we also need to, of course, to minimize the cost and to scale up these products. But this property here, which is low dark current, is one of the main, I think, properties or mandatory property that we need to fulfill in this case for these devices. Some of the commercial semiconductor-based X-ray detectors in the market nowadays. We can see the silicon-based, germanium-based. They are good. I have to say they are good. They present some properties that feel this needed that we require for the conversion of X-ray, but they have also problems regarding, for example, the case of silicon is the atomic number, which is low, so the sensitivity is low. Then the germanium, which is the gold standard for saying of X-ray detector, have this problem of the band gap, which generates so thermal noise, and we have sometimes we need to use a nitrogen and a cryogenic cooling system in order to use those devices, the germanium-based X-ray detectors. And we also have cadmium telluride, which is good and have an adequate band gap, but of course it is expensive to prepare these kind of devices. So this is some of the idea of how of what we are dealing in nowadays. So this is like a summary of what I'm trying to explain. It's like the ideal X-ray detector need to have one detector quantum efficiency, which means that the radiation energy absorbed is completely converted into an X-ray, into image information. And of course, the modulation transfer function, which is connected to the spatial resolution of the number of pixels per square centimeter, it needs to be high, and the state of art of the semiconductor device present a higher energy resolution, but they have problems in terms of sensitivity and dark current. And the scintillator are here. They have maybe inadequate resolution energy, but they have problem with the efficiency. So maybe we need to design the next generation of X-ray detector needs to be here. The ideal detector, of course, is hard to get here, but this is our purpose of this work. So in order to, with all that information in our mind, we have perovskite materials, and perovskite materials are quite good, and they are performing quite good in the field of solar cells, LEDs, and they are performing pretty well in the field of X-ray detector as well. So the property of perovskite has been extensively studied. We can observe that perovskite present a strong stopping power, radiation hardness. We have the lead in the structure. So for us, in the field of X-ray image is good because we have a strong stopping power and we can stop X-ray with this high atomic number. Perovskite present good transport properties like the long short-array diffusion length, large mobility lifetime product. So this is quite good, I have to say. And we also can use perovskite at room temperature. So this is another advantage of perovskite. And it's quite impressive. And this is like the research paper, the cumulative number of research paper in this field, how in the last year, the number of paper and proposals about the perovskite materials for X-ray detection have increased. So this is telling something, and it's like it's a field in progress. Of course, the first paper about this were single crystal, the property of the single crystal, the good transfer property, which means high charge collection efficiency and can be transduced to a high sensitivity. We also observed some reports about polycrystalline films, so showing high sensitivity and also high charge collection efficiency. Even double perovskite has been used. But of course, not all that glitter is gold, and perovskite is a mixed ionic-electronic semiconductor, and the electronic ionic nature of these materials and the migration of these mobile ionic species may generate dark current instability. So this is I think the bottleneck of this technology, the long-term stability of the perovskite materials for X-ray detection. And mobile ions have been extensively studied. This is not a new topic at all. Transition energy, formation energies has been reported. Even the mobility of this perovskite diffusion coefficient. So basically, these ions migrating and how they are connected to the dark current is one of the, I think, the topics nowadays in this field. So we need to take a look to the ion migration process in order to understand how these affect the long-term dark current stability of those devices for X-ray detection. So this is the goal of to summarize, I think, the understanding of the chemistry of this metal halide perovskite, some mechanisms governing the electronic operation, to propose some mechanisms, and of course, how the electronic ionic migration process may affect this dark current stability and this long-term electrical stability of the device. I will talk very shortly about how we develop these perovskite devices. Then I will present, I think, and this is the most important part of the work, how we face the study of ion migration process, first to focus on ionic diffusion and then ionic drift in this material, and then some conclusion and what I think is the next future, or what I think is the future outlook of this field. So briefly, I will say that we prepare two kind of devices, single crystal and then polycrystalline devices. I have to say that I was more involved in the synthesis of the single crystalline samples. It was in collaboration with our with SIA, the institute in France. So we prepared these single crystals, and we also prepared the polycrystalline samples in collaboration with Siemens Healthineers. And they, of course, the details about the synthesis procedure is published in this very nice paper, and is also they also have a patent. So I will not go into details, but I have to say that this second procedure is just mixing powders and pressure this powder with the right temperature and pressure. Of course, we need to play this in order to optimize, and then the electrode deposition. You want to go deeper in the synthesis, you have the link here. But in the single crystal preparation, the preparation of monocrystal is quite a standard method. It's not new. It's the ITC, which is based in the rotor solubility property of certain perovskite in certain solvents. In this case, we use methylammonium bromide in DMF. The procedure was made, one of the main part of this procedure was made in the IPB, Institute for Photovoltaic in Stuttgart, during my research stay at the group of Professor Michael Saliba. And I have to say that at the beginning of this process, I was quite worried because it seems like when we check in the literature, it seems like it's quite easy to grow single crystal, but it's not easy at all. And we need to optimize many conditions. At the end, we ended with this polycrystalline sample with not cubic shape. So we changed to larger and wider vials in order to let the crystal to grow in a big, large area for sale. And we obtain a better quality crystal, but not cubic shape. So we start thinking about what to change, and we ended with this slow seeded grow and with using seeds during the crystallization process. But of course, we need to optimize this in order to obtain a smooth surface, because as you can see here, the surface was quite rough. So we again optimize the heating rate, we play with different heating rates, and at the end we found the optimized method for saying, and we grow high quality single crystal. Of course, once the crystals are grown, we need to characterize them, and of course we did the XRD diffraction spectra. We did also XRD2D rotation spectra in order to measure the degree of crystallinity of our sample. And this is quite good for people working in the field of single crystal, because it's not enough to have the XRD pattern. Sometimes you need to know the degree of crystallinity of your single crystal. And we also perform, of course, as UV spectra and PL photoluminescence. We were quite sure of the quality of our samples, but of course, before any deposition of electrodes, we need to polish the surface because sometimes we have inhomogeneities on the surface of our single crystal. So next step in the preparation of this device was to think about the architecture because, of course, perovskite material present many stability issues. We can observe that there are many papers in the literature talking about device degradation promoted by light, by humidity, oxygen. So, and there are also many reports trying to design strategies in order to solve all this problem. So, it's quite know this to select the electro composition is quite hard. It's well known that gold may migrate to the perovskite and react at the contact, so gold was discarded. We also observed some silver electrode-induced thermal degradation, so we also discard silver. And we ended with this very nice paper about the use of chromium, which can enhance the stability of the perovskite device in solar cells, for example. And this other report also shows how this prolong the device lifetime in ambient temperature. So we were quite sure that chromium was a good choice. So we start thinking about the architecture, and we observe that again, the vertical device present the faster response due to the electrode spacing. So we designed our first approach was to use the simplest configuration. It was ohmic junctions based on symmetric electrodes of chromium. And the second approach was the use of asymmetric electrode because we observed that the use of asymmetric electrodes can help us with the dark current of the device. This very nice paper of Professor Kanatsidit shows how at reverse bias we can observe the lowest reverse current. So this chunky junction based on asymmetric electrode was our second options. So basically we use platinum, which is quite is a non-reactive electrodes with the perovskite layers. So finally, we have our device, our single crystalline device, our polycrystalline device of methylammonium lead bromide of methylammonium lead iodine. So we were quite sure that now the main idea was to study the ionic process. So first we focus our attention in ionic diffusion, and for that we use impedance spectroscopy. And impedance spectroscopy is a quite well-known technique. It's quite used in my previous group at the Institute of Advanced Materials. So this protocol of impedance spectroscopy was developed during my thesis. I have to say it was a new way to measure ionic diffusion, because here, as you can observe, we first we pull the sample to different bias or one bias, depending on what you want to see. And then we left the sample to relax at 0 volt bias, or what we call short circuit condition. And of course, we can observe how the recovery bias or the resistant relaxation is made. Sorry, my light, I need to move. Okay, yes. So basically, this is the protocol of impedance spectroscopy. If someone is not familiar with the technique, impedance spectroscopy can help you to measure the sample response to an electric field and in a frequency range. So basically, we focus our attention in the recovery bias, and this is what we observe. First, as you can see here, when we pull the sample at different bias, we have this kind of accumulation of ions at the beginning, and we have two zones of higher and lower carrier density. So then when we apply zeroable bias, or when we remove bias, short circuit condition, we can observe how the resistance decrease under steady state resistance. It's like we observe how the ions diffuse and they shift the electronic conductivity during the recovery bias. And this can be observed by impedance spectroscopy. If after 24 hours, we can see how the resistance relaxation is at this value of resistance. So basically, we can, with this relation here, the resistance, the high frequency resistance, we can observe that this resistance goes, it changes it maybe in one order of magnitude. So this is basically what I'm trying to say, is that the ions shift, the ion diffuse and shift the electronic conductivity. So the ions modulate or vary the electronic conductivity in our device. So this is the way that we try to extract parameter. When we plot this radio of resistance as a function of the square root of time, we can extract this diffusion coefficient and ionic mobility. And this is the order of magnitude of both parameters. And because we were these values were obtained before, we can observe that they are in good agreement with those values reported in the literature, but they can be presumably connected to the halide vacancy. At this point, we were not sure, but of course, I will go in the next slide, I will try to explain this. So I think the main idea of the ionic dynamic doping mechanism is how these ions may vary the electronic conductivity during the diffusion. So basically the electronic doping profiles depending on how is the ion bulk distribution. And we can record this by observing the resistance shift. This is the main idea of the ionic dynamic doping mechanism. We use the same approach in our micro-crystalline samples or pellets or methylammonium iodine pellets. And we did the same experiment. We pull our sample at different bias, and this is just the recovery bias spectra, impedance spectra. So we can observe here how the impedance after 12 hours goes to this value. And if we plot, again, this radio of resistance as a function of the square root of time, we can extract again the diffusion coefficient. And as we can observe here, this value is in agreement or is the same that those values found for our single crystalline sample. So then we have to see, because we were, of course, we just, at this point, we were studying ionic diffusion just by using impedance spectroscopy. So we need another approach. So in this case, we use the chronoamperometry measurements, which is called the long-term current transient in our devices. And you can observe here, we apply a voltage and then we left the sample to relax at zeroable bias, again, short circuit condition. But in this case, we record the current of our device. And as you can observe here, this is 10 volt. This is the current the current response at 10 volts, and this is the short circuit response. The current response at short circuit. It's very noisy because it was almost in the limit of the instrument. But as we can observe here in this plot, this kind of pattern, which is current proportional to the square root of time, is again a diffusion pattern, a diffusive pattern. This has been reported before, and from here we can extract again the diffusion coefficient, and again we found that is the same, that those diffusion coefficients found in our impedance measurement. So both measurements were consistent, and we were quite happy with that, per se. So again, this diffusion coefficient has to be in the next slide. I will explain how we connect this to the migration of these halide biases. Well, finally, after the host protocol of the ionic diffusion, we start thinking, of course, if we were use those X-ray detector under higher electric field, we need to observe how is the ionic drift, because this is important. So I have to say that this protocol is new, and it was quite hard. It took me months to develop this protocol in order to obtain reproducible and reliable response. And it's quite hard in perovskite. All people working in perovskite should know this fact, that it's quite hard to obtain reproducible and reliable response. So at the end, I found that this protocol of using different voltage steps and applying a short circuit current after every voltage step, it was the way to measure and to obtain the long-term current response. So in here, I plot, and this is, I think this helped to understand, this is the steady state current, which is, as you can see here, is the value after the exponential increment. The current saturates until a steady state value. And this steady state current, we plot this JB as we compare. In this plot, we try to compare this steady state current value with the normal JB at a fast scan rate of our device, and also with the ionic current. And the ionic current, this response here is extracted from the short circuit current. And this is a new way to obtain some ionic parameters. As you can observe here, and this is a conclusion of this plot, these ionic currents are negligible in comparison to the electronic currents, as you can observe in terms of value. We have nanoamperes and we have microamperes here. So this is good. Okay, they are negligible, but they influence the long-term current response, because of course this response exponential increment of this current exponential increments are pure electronic, but this time constant is too, have to say, too large. The values are too large, so this has to be connected to ions. So this is the main conclusion here. The mobile ions influence significantly this long-term electronic transport process by modification of the charge density profile. So, of course, the current is electronic, but the kinetics of this response is governed by ions. This is the main conclusion here. Of course, we can try to use many approach and to try to propose hypotheses about how this may occur, and we have these three that we think that can be influenced. It can be due to the increment of defective electronic doping. It can be due to the dynamic doping of something happened in the contact caused by this accumulation of ions at the interface, or maybe the three processes can occur at the same time. So this is quite, of course, this is just our approach or way to see this process. But I think the main idea is that, of course, again, we are observing that the ions are influence our electronic response. So then, in order to have more statistic measurements, and we start thinking about, because the long-term stability of the methylammonium lead halide perovskite is composition dependent, or polycrystalline sample, we start studying only MAPI, and we start thinking maybe methylammonium lead bromide is another suitable way of study this kind of perovskite, because it has been reported how methylammonium lead bromide is, because this favorably cubic structure of methylammonium lead bromide is more stable at room temperature compared to this distortional configuration, cubic configuration of this methylammonium lead iodine. So basically, we start thinking about to compared both composition and the exponential increment that we were expecting at the beginning of our measurements using the protocol that I presented before, I observed that the response of our device were much more complex than what we observed before. This kind of response, this kind of feature on the current transient response were quite new. And we observed that, for example, in the case of methylammonium lead bromide, same composition, but different crystallinity, we have almost the same shape of our current time response. But when we compare this methylammonium lead bromide with methylammonium lead iodine, with both microcrystalline samples, so different composition, but same crystallinity, we can observe that we have this feature here at these higher electric fields, this second step here. So we start thinking about this. So it has to be related with the chemistry of the defect formation between the compounds. It's not related with the crystallinity, it has to be related with the composition. So we start thinking and checking in the literature, and we observe that yes, in the case of bromide-based perovskite, it sometimes happens that we can observe the suppression of this bulky cation. And if we look at the periodic table, we can see that the electronegativity decreased down in the group. So if we think about this bromine lead bond and iodine lead bond, we can think that it's shorter in the case of bromide-based perovskite, and this has been reported and is consistent with our measurements by transient iodine. This is a very nice paper, and it shows how in the case of bromide-based perovskite, the bulky cation, the methylammonium cation, can be suppressed of course, in certain condition at this bias. As you can see here, this is a summary of what I present. So basically, we have a higher structure stability in our bromide-based perovskite. Then we, again, using this relation, we can extract ionic mobility, and we can observe here how in the case of iodine perovskite, we have almost the same dependent with the electric field, is constant, the dependent, with the electric field, but the case of bromide-based perovskite is again, is completely different. We have a different dependent field. So in this case, methylammonium iodine is independent of the electric field, and this case is dependent of the electric field. And we can extract again these ionic mobilities, which are in agreement with those values reported in the literature. So again, finally, I would like to conclude, I'm almost in time. So basically that about the experimental findings, we found that the ITC method works, but we need to optimize this method. The faster unseated heating profile didn't work for us because we ended with many polycrystalline samples, but the case of the slower seating heating profile works for us, and we obtain good single crystal with high crystallinity, with a high degree of crystallinity and high reproducibility of our experiments. We use symmetrical single crystalline samples and asymmetrical microcrystalline perovskite in order to minimize the dark current. From these ionic diffusion measurements, we can observe that there is a coupling, as I mentioned before, between the electronic properties of our device and the ionic properties. And this coupling relies on this ionic dynamic doping defect, which is caused by these mobile ions that act as mobile dopants. This coupling between the ionic and electronic transport establish the time scale of the electronic current, the kinetics of the electronic currents, and we observe from the ionic drift that using a robust and reliable current transient protocol, we can obtain reproducible and reliable respond. You can observe here the different cycles and how we can observe this a reproducible response. And as a main conclusion is how this measured current is electronic, but the kinetics of this response follow this slow ion rearrangement. And finally, how we can see that there is a difference when we use different composition of perovskite material, and these differences are connected to the chemistry of the defect formation between both compounds. This is just very briefly, I would like to show how the final divide looks. This is the paper and the sensitivity of the divide, which is quite good compared to the commercialized X-ray detector. And this is the single crystal. This is still a work in progress, but we are quite happy that at the end we ended with this all devices. Just to conclude, ion migration was confirmed. I want to highlight that we proposed the dynamic doping effect by measuring ionic diffusion. We obtained this reliable protocol, and we have proof that this coupling between the electronic ionic current is connected to the slower species and how this species may condition in the kinetic of the electronic response of our device. All this information is important in order to, at the end, understand the electronic operation and the long time scale that current stability of this device. And this can help us to progress into the device physics and the operating modes of these materials. Just to conclude, this is the chart that I present in the first slides, and this is maybe our devices. We are close, I think, we are close. Of course, we need to minimize the dark current. Dark current is still the bottleneck, as I mentioned before. How we can solve this, and I feel this is the perspective of what I think is the next step in this field. We can use fully inorganic perovskite. We can also use interstitial doping by using multivalent cations. I read this paper about the use of neodymium, another multivalent cation. We can use additive or interlayers in order to reduce defect density, or 2D, 3D perovskite, or why not, if in the field of solar cells we are using lead-free perovskite, we can try to use in the field of X-ray detector this novel lead-free perovskite for hard radiation. And so many, of course, we can have many ideas about it, but of course, it is important that we still need to solve these dark current problems. Finally, I would like to thank my group at the Institute of Advanced Materials, my previous group, and my supervisors, Professor Marise García-Batlle, Dr. Antonio Guerrero, my collaborator, Dr. Osbel Almora, my group at the Institute of Advanced Materials, and I want to thank my current group now, which is in the UNC, because Professor Jinson Huff has given me the opportunity to continue learning about this, I think, very interesting field, and which is growing every day. So thanks to you for listening, and thanks to the organizers.